Greetings, Algebra 2 Trig people. Next section is 6.5, and that is called Geometric Sequences. And just one friendly reminder, and that is that you should be taking some notes while you're watching these videos, so hopefully you have something available to write with. So we've been doing a lot with arithmetic sequences adding, so what's up with geometric sequences? Well, let me show you one to get you thinking about it. So here we have one. 5, 15, 45. That is a geometric sequence. So if you applied what you know about arithmetic sequences to this, you would say, well, what do I do to 5 to get to 15? I add 10. So then I come over here and I say 15 plus 10, oop, that's not 45. So clearly something different is happening here. And my guess is with a little bit of thinking you would probably figure out that what's happening is we are multiplying by 3. So basically what a geometric sequence is going to be a sequence that we continuously multiply or divide by the same value. And if we want to figure out what that value is, we take a term and we can divide it by the term before it. Say we said take the third term, divide it by a sub 3 minus 1, that would be the second term, and that is going to give us what we call r as opposed to d. When we had a common difference, now we have r, and that is called the common ratio. So if we come back over here, we can clearly see that's to be the case. If we picked 45 divided by 15, that does equal 3, or we pick 15 and divide that by 5, that also equals 3. So we need to start thinking about something called the common ratio. Okay, so similar to arithmetic sequences, we have what we call a recursive definition. And this word might seem a little weird to you, but recursive just means it is dependent on the thing before it. So a recursive definition means that a sub n, the term that you care about, is just going to be equal to the term before the term you care about times the common ratio. Now that is a fine way to define one of these things, except when you want to know what the 253rd term is, because then you have to go through 252 terms to get there. So that's why we also have what we call an explicit, or sometimes it's called the general definition. And that's when we actually figure out a definition that allows us to get to any term without having to go through every single term along the way. And basically all we need to do is we need to figure out what's in the first position and multiply by that common ratio one less number of times than the position we want to get to, for the same reason that we did that when we were using our common difference, and we'll play around with that here in a second. So let me go ahead and do another example. So given this sequence 4, 12, 36, 108, 324, ... You may be asked to just answer the question, is this a geometric sequence? So starting to get familiar with geometric, then you should say, well, let me think, do I continuously multiply by the same number? So you probably look at the smaller numbers and say, well, yeah, 12 divided by 4, yep, that's 3. 12 times 3, yep, that's 36. 36 times 3, yep, that's 108. 108 times 3, you might need to use your calc to check, but sure enough, that does equal 324. So this is a geometric sequence. Then you may be asked some question like, what is the 10th term of the sequence? And so this is where we don't want to get in the habit of actually having to go out 10 terms. So just for the purposes of thinking about that a little, let's see how many terms we have here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we want to get to this position here. So rather than using a recursive definition, using the explicit or the general definition, basically the thing in the 10th position is going to just be equal to whatever is in the first position times the common ratio, which is this 3 that we continuously multiply by, raised to 1 less than the place that we want to get to. So that would be 10 minus 1. So the 10th position is going to have 4 times 3 to the 9th power. And you can go ahead and put that in your calc and you should get a number 78,732. So just to try to make this really clear, so it's not all so much about memorizing. I mean, the equation is a sub n is equal to a sub 1 times r to the n minus 1. But the reason it's that is because if this is the first position, to get to the 10th position out here, I go 1, 2, 3, 4, 5, 6, 7, 8, 9 steps to get there, as in 9 multiplications of 3. So it has to be 1 less than the position that I'm trying to get to. Okay, another interesting thing about geometric sequences. I'll just give you one here. A little short one, 4, 20, 100, just to think about for a minute. There is something interesting about the number that is in between two numbers in a geometric sequence. And that interesting thing is that this is called a geometric mean. And this is something you probably saw in your geometry class. And if I want to think about a geometric mean, it's actually something I can think about in a proportion. And so the geometric mean finds itself in this position in a proportion. And then these two numbers find themselves in these two positions. So if you remember, in a proportion, we find that the product of the means is equal to the product of the extremes. So 20 times 20 is 400, and so is 4 times 100. And so this fact sometimes actually allows us to figure out different terms that are in a geometric sequence because of this particular relationship. So let's make this a little more complicated to prove that point. So say instead of that nice 4, 20, 100, let's say that we had a 4, and then we had 3 spaces, and then we had a 100. So as long as the geometric mean, as long as it's actually right in the middle of two other terms, we can use the method that I just showed you to figure it out. So we know hopefully that this is going to be a 20, but pretend that we didn't. So we would say 4 is to x, as x is to 100, and we would figure out that x squared is equal to, 400, and then x would be equal to 20. Technically it's equal to plus or minus 20. For now though, I'm just going to think about the positive. So that is equal to 20. So then if I want to figure out what goes into this position here, I can do the same thing again, because this position is the geometric mean between 4 and 20. So I'm going to put a 4 here, an x here, an x here, and a 20 here. And now I get x times x is x squared, and 4 times 20 is 80. And I get x squared is equal to radical 80. So x then is equal to, if you think, well, I'll write this out, radical 80. So then pulling out the biggest perfect square, which would be 16, x is equal to, and this is plus or minus technically, plus or minus 4 radical 5. Now, for right now, I am just going to think about the positive aspect of this. So 4 radical 5 divided by 4 then is radical 5. So it appears that the common ratio is radical 5. So if I take 4 and I multiply by radical 5, I get 4 radical 5. If I take 4 radical 5 and I multiply by radical 5, I get the square root of something times the square root of something is of something. So I get 4 times 5, which is 20. When I take 20 times radical 5, I get 20 radical 5. And then when I take 20 radical 5 times radical 5, I get the square root of 5 times square root of 5 is 5, and 5 times 20 is 100, so it works. I would just leave this for you to think about a little. We'll talk about it in class at some point. Could negative radical 5 work as a common ratio? Okay, a couple more problems to think about here. Given another example, this problem. Find 4 geometric means between 5 and 1,215. What could we do? So I'm going to go ahead and draw a little sequence so I can think about it. So this is as much about vocabulary as anything, and realizing that really what I'm trying to figure out here is a geometric sequence. So I need 4, so I'm going to put 4 spaces. 1, 2, 3, 4, and then the number 1, 2, 1, 5. Now if you'll notice, I can't get one that's right in the middle here, so I'm going to go about this from a different perspective, and that's what I'm going to do in this case. Is I'm going to use my explicit or general form, where I know that a sub n is equal to a sub 1 times the common ratio raised to the n minus 1 power. So I actually have this number 1215, so I'm going to write that down here. And I know what's in the first position, which happens to be 5, and I don't know my common ratio, but I do know what position the 1215 is in. And so that is in position 1, 2, 3, 4, 5, 6. Therefore, it takes me 5 steps to get to that position. So solving this equation here then, I can figure out what the common ratio is. So if I take 1215 and I divide that by 5, I get 243 equal to r to the 5th. Now, it should be comfortable, hopefully, if it said r squared equal to 243, you know you take a square root. So if it says r to the 5th equals 243, I'm going to take the 5th root. And if you don't know the 5th root of 243, you can put a 5 on the screen and use your calculator to figure out the 5th root of 243. And that turns out to be r is equal to 3. And so now I can fill in the blanks. So 5 times 3 is 15. 15 times 3 is 45. 45 times 3 is 135. And 135 times 3 is 405. And I am going to leave it right there for now. We'll talk a little more about some real-world geometric sequences in class.